So hello, I'm Caro Derkenne. I'm a first year PhD student from Macquarie University, and I'm giving the MAGPI survey overview on behalf of the MAGPI team. So as I go through the talk sharing the updates of what we've actually managed to do with the data so far in our science progress, I thought I'd highlight the really cool data that we've got that's underlying that science progress. So this is actually one of the MAGPI targets, and this is the full Muse field of view. So we've got some quirky galaxies in the sample. You can see these massive tidal arms here. And one of the cool things that we're doing in this survey is this image is actually formed from the Muse cube itself. So we're trying to use the Muse cube data as the basis for some of our photometric results. So what is the MAGPI survey and what is its goal? Its aim is to study galaxy properties in the Middle Ages of the universe using integral field spectroscopy. So it's a Muse large program survey. The PIs are Caro, Claudia, Trevor, and Emily. And just using a quick Slack channel count, I think we've got over 50 MAGPI team members at the moment. And that's not just in Australia, that's distributed around the world. And team contributions are made through 4 main working groups. So that's the Absorption Line group, the Emission Line group, the Master Catalogue group, and the Theory group. So it's a distributed leadership model, which means that all team members are really able to make a meaningful contribution towards the science of the survey. Eventually, we will have 56 fields observed with 4 hours of on-target observation time. That has been delayed a bit because of the COVID situation. But it's going to be a really lovely sample when it's finished. And we've also got 2 supplementary fields, 2 clusters, Able 2744 and Able 370. So we're looking in the redshift range of about 0.25 to 0.35. And that's looking back in cosmic time in about 3 to 4 gigayears. So like I said, we've been a bit delayed because of COVID, but we've got 18 fields observed so far. And Andrew later is going to run through the actual numbers of how they're distributed in Redshift. Because the survey uses ground layer adaptive optics, we've got really lovely seeing, so 0.6 to 0.8 arc seconds. And a lot of work is really going into understanding that PSF so we can get the best possible results from the data. The targets are all pretty massive, the primary targets, and they were picked to span a range of environments so we can try and disentangle that role of environment using the survey. But in addition to those primary targets, we've actually got a huge sample of satellite galaxies and emission sources up to quite high redshifts. So it's going to be really fun playing around with the other galaxies that aren't just the primary ones. So I show here one of the kinematic fields for the stellar kinematics. The tick labels are arc second, so you can see relative to the PSF size, which is less than an arc second, we're resolving the objects really nicely. And these are the kinematics from Francesco. So the science aims of the MAGPI survey is really to question how did galaxies go from being quite compact and highly rotationally supported in the high redshift universe to this rich morphological mix that we observe today. And there hasn't really been a dedicated observational campaign to look at this time in the universe. So it's relatively unexplored. One of the things that I'm also really excited about with this survey, and something that Kate's going to talk more about, is that every step of the way we're going to have a detailed comparison ready theoretical data set. And that's going to be really important to look at what are our observations saying science-wise, what is the theory saying science-wise. In particular, the main science goals, and there are projects within this, but the main science goals that MAGPI is trying to answer is how important is the role of environment and that question of nature versus nurture. Understanding the role of gas accretion and merger activity. Looking at the sources of energy and feedback activity, and also the metal mixing history of galaxies, because that can be a really good indicator and constrain mass assembly histories as well. So for the central galaxy here, I showed a metallicity map that was made by Sam Vaughan. And that's going to be used to help look at stellar populations and metal mixing histories and gradients and things like that. So I'll start with the emission line working group. So this is the same galaxy that I've been showing, but looking at the emission lines now. The working group has released maps with 22 emission lines measured, and that's actually out to a few effective radii in light. So this is the primary galaxy, at a redshift of 0.3, but you can see there's actually a really high redshift one of about 0.7 as well. So we are picking up on those satellite galaxies, which is really cool. The emission line science is going to be supported by a recently accepted ALMA proposal to measure the molecular gas content of 14 of the MAGPI primary targets. And that's going to be the first detection in this sort of transitional period of the universe of CO. So that's going to be really exciting when that new data comes in addition to what we've got from MAGPI. So this emission line data is going to be used to really understand quenching in this epoch. We can understand dust attenuation as a function of redshift. We can look at spatial variations in the interstellar medium of electron temperatures and explore metallicity gradients as a function of redshift to large radii. So really looking at the drivers of galaxy evolution in these universe middle ages. So sticking with the emission line working group for the moment, I wanted to highlight some early science results done by Marcy, who's a PhD student at ANU. And while we're going through these preliminary science results, I just do want to highlight they are a work in progress, so don't hold us to anything that we have found here. So this has already been spoken about quite a bit today, but there's a resolved star forming main sequence. So there's this tight relationship between the star formation rate and the stellar mass density on the x-axis here. So the blue line is showing the best fit relationship to the star forming population of MAGPI galaxies. So this is using emission line data, and we've also got mass maps for the MAGPI fields from Ned Taylor. So the blue pixels are more star forming than the red pixels, so you can see two nicely resolved populations and potentially also a starbursty population. And this sort of science looking into the main sequence relation and exploring questions of quenching with it has already been done with MENGA. So we've got a really nice redshift, like local universe reference sample to see how things are changing with redshift. Like I mentioned, we do have the primary targets, and we've got some really exciting science going on with those primary targets, but we're also getting serendipitous Lyman alpha sources at the really high redshift universe. So now redshifts of about 6. And Lyman alpha emitters are interesting because you can use them to trace large scale structure in the early universe and also constrain the really faint end of the luminosity function. So some work that Anshu has been doing is to look at whether there's any spatial connection between the Lyman alpha emitters in any of the MAGPI fields. And she actually found, this is the spectra of some potential Lyman alpha emitters. You can see that they've all lined up really nicely. So these are the potential sources, and they're actually all within 200 kiloparsecs of each other on in the universe, I guess, on the field. And so this is a suggestion, which still needs to be confirmed, but it's a suggestion that there's some large scale structure at that universe that these sources are tracing. So that's some cool science to follow up on. Moving now to the absorption line working group. We've got 2-moment and 4-moment kinematic maps to work with. And for some of these, it's really cool. They actually go out to more than 6 effective radii. So all these population trends and questions that we've got, we can really trace them out to the outskirts of these galaxies. So we're going to have resolved maps of the stellar populations. We can look at things like the stellar dynamical mass to light ratio as a function of redshift, and also how that can be used to constrain and ask questions about the initial mass function. A project that's really in comparison, like strongly comparing to simulations, is looking at the evolution of dynamical substructures in galaxies. And I think this has also been something that's come up a few times today, but the importance of looking at angular momentum and tracing that and using that to constrain galaxy evolution pathways. And just that general idea of looking at stellar populations and galaxy dynamics. And we can also question the role of repeated gas pore mergers and where this transition radius between in situ and ex situ material occurs. So I just wanted to highlight how nice the data actually is that we've got from this survey. So this is the stellar velocity field and the stellar velocity dispersion field. So what I'm really interested in with the MAGPI survey is related to that idea of gas pore mergers and ex situ and in situ material. So I'm using the MAGPI data to study the total mass density slopes of early type galaxies. And the total mass density slope is this interesting quantity. It's the change in mass density with respect to galaxy radius. And we know from simulations that it's correlated with other interesting galaxy properties like dark matter fractions, but it's also an indication of gas pore merger activity. So simulations show that the total mass density slope is quite steep at higher redshifts, and merger activity, gas pore merger activity in particular, drives it towards slope values of about -2. And we know in local universe observations using, for example, SLUGS data, Atlas 3D data, and also MANGA data, that they all really quite agree well with the predictions of simulations. However, when we used identical methods as in the local universe at higher redshifts using massive cluster galaxies, we didn't find any evolution in that density slope towards steeper values. That could be for a few different reasons, one of which is we need to go out to higher redshifts. It could also be that there's a role of environment in the population mean of that total mass density slope. So maybe we need to not just look at these massive cluster galaxies, but also look at field galaxies. And that's where the MAGPI data is going to come in to help look at that role of environment. So
1 minute.
cool, thank you. I just want to show here one of the dynamical models that I've made so far using MAGPI data. So here is the observed VRMS field. So that's the quadrature sum of the stellar velocity and stellar velocity dispersion. And then this is the modeled VRMS field. So this is using a GEANS anisotropic mass model. And what we're finding is that with the MAGPI data, you can really tightly constrain the total potential. So I just want to point out this is the constraint in that parameter space. So I'm quite excited to see what the full sample of this MAGPI data can reveal. So far, as a very preliminary result, we are seeing a suggestion of a difference in the average slope with environment. So I'll leave you with this slide just to highlight that we do have our survey paper out at the moment, so you can go and read that. And you can also find out a lot more about the survey on the survey website. So I'll take any questions now.
Thanks, Caro. That was bang on time. So there's already a question on Slack by Katie, who asks, how deep do the data cubes go down to? Also, I don't have a super clear understanding of the types of galaxies in the survey. Do you have a handle for the distribution of the types of galaxies in MAGPI, the ratio of star-forming / intermediate quiescent passive type of galaxies?
Okay, so I can't give a very clear answer for either of those questions. In terms of data depth, we have decided to use the MAGPI fields, like the Muse cubes for the imaging, because they do give a better depth than other alternatives that we've got out at the moment, like the HSC data. But I don't have an exact number off the top of my head. I think Trevor is someone to follow that question up with. In terms of the morphology, it really is a mixed bag. There's a lot of early types, a lot of spirals. There's some really fun ones that I don't think anyone quite knows how to study because they don't fit nicely into a classification scheme. Again, with the star forming, I don't have that number off the top of my head.
Right, thanks. Are there any more questions? Okay, there's another one by Julia who asks, the data looks amazing. Do all the observations reach radii over 1 RE?
I mean, all the primary ones should, because that's how the survey was designed. Certainly with the satellite galaxies, they won't, not all of them, but we have been surprised. I mean, not surprised, but it is lovely how many satellite galaxies and background sources and things there are in the data that we weren't counting on, but they are there to also explore.
Right, okay, thank you.